So welcome to this class. So in the last class we have just briefly reviewed the reconstruction, how to proceed with the reconstruction from the obtained data. Now in today's class I will show you some of the calibration methods which are used to calibrate the reconstruction what you have done from the APT data. Okay, so the accuracy of the final reconstruction is derived by precise determination of xi, image compression factor, field factor, your efficiency, and also the radius of curvature. These are the four factors which are very important and should be precisely measured to accurately determine your final reconstruction. Okay, so calibration can be performed by using film. So in an atom probe tomography, if you use you can use, there is a counter electrode, there is a detector, so you can actually use the imaging gas in the same instrument, and actually you can do the field ionization microscopy. Fine. So at the start of the experiment, so that to determine these values. Okay, so film can be used to determine the reconstruction parameters, which are these reconstruction parameters. As I told you, these depends upon the specimen shape, electrostatic environment, then radius of curvature, shank angle, field factor, and image compression factor. So these all parameters can be determined by using the film. So we'll come step by step with this. Just briefly, it might be a revision that we discussed for the last couple of classes. Okay, so in film you can see that a typical film image, you have a concentric rings. Okay, and these rings corresponds to certain crystallographic poles, and these concentric rings are nothing but the atomic terraces. Okay, if you identify these crystallographic poles, pole 1, pole 2, so crystallographically they have a certain angle between the two planes. Okay, crystallographic angle, which is a constant, which can be measured by the cos theta. Correct. Now actually in experiment also you can measure this theta crystallography or theta observed. Then you will get the image compression factor as estimate as theta crystallography divided by theta observed. Okay, so this way we can identify the xi or the image compression factor. Okay, so this is the first, image compression factor. Now second is radius of curvature. Okay, so in the film you can see these are all the rings which is having a certain diameter. Okay, so ring pattern is used to derive the radius of curvature, that is by the size of the terrace, which is actually inversely proportional to the radius, local curvature, radius of curvature. Okay, so as in the previous in one of the previous class we have derived this equation r0 1 minus cos theta n, which can be equal to n dhkl. If you identify that particular pole HKL, and you can actually calculate the R0 with this equation. Okay, so this is the radius of curvature. Another thing is shank angle. Third is shank angle. How to determine the shank angle? So if the radius has been determined, then as we know that due to the geometry, so if this is the particular R1 and if this is the R2, so radius has evolved from R1 to R2, and if you we can this is the time 1, this is the time 2. Okay, so if the number of atomic layers between these two are measured, which is equivalent to a ND spacing of that particular pole, then your shank angle can be estimated by the formula sin alpha is equals to R2 minus R1 divided by R2 minus R1 plus N DHKL. Okay, so this is how we can measure the alpha, which is a shank angle, by the evolution of the radius at two different instances. The fourth one is field factor. So if the radius is measured, so this I am talking in the FIM, correct? Remember this I am talking in FIM. So if the radius is measured, if you know the radius, and assuming that the electric field at the apex is F, so your F is equals to V divided by KFR. Okay, so field is assumption. What is the assumption? It is assumed that in film, I remember I am talking about film, where the field required to evaporate atoms from the surface is known to vary due to the presence of imaging gas in that particular field. Okay, so this is the assumption which we made. So whatever the field required to field evaporate the atoms from the tip surface is known to vary, and this is due to the presence of the imaging gas which is present on the tip surface. Okay, so that's why due to the presence of this imaging gas, the precise determination of field is not straightforward. So determination of KF by film is little bit difficult. Okay, but in atom probe this KF value can be determined, because your field ionization, your evaporation, your field evaporating the actual ions which are present, actual atoms which are present in the tip surface. Okay, so the film can be used for these four parameters. Now by using FDM, this is called field desorption microscopy. This is nothing but atom probe tomography. It's a estimation can be done for these parameters also. Okay, so the desorption image which is formed by the arrival positions also reveals the crystallographic information used in the atom probe, which is similar to the film. So they also have a desorption image. Where there will be a change in the density or appearance of rings, concentric rings, and these rings are corresponds to the ions which are field evaporated from the tip surface. Okay, so this is a field desorption microscope. Okay, so remember in film you are actually creating an image from an imaging gas, but in FDM actually your atoms are ionized and get desorbed directly from the surface of the specimen. Okay, so these also can have a concentric rings, appearance of ring structure around the main poles. So similar to film, you can actually also measure the Xi value. This is related to the theta crystallography by theta observed. You can get the R0 can be determined by the ring structure depending upon the terraces. Correct. So here the R0. So in that equation you have a theta n, which is the angle between the center and the edge. of the nth terrace around the pole. So remember the equation in the previous equation, we wrote R01 minus cos theta n equal to n dHL. This theta n corresponds to the angle between the center and the edge of the nth terrace around the pole. Okay, so before we determine the R0, it is necessary to determine the xi and also the kf, which is the field factor. Okay, so kf, as we explained, this is V equal to Fr, and we can actually, during for the FDM, we can estimate the kf or the f by the, we can estimate the f by the Kingham diagrams or plots. From these plots, actually we can accurately determine the electric field which is present near to the tip surface based on the species or the specimen. Correct? With this, we can determine the actual value of the kf. Okay. Now, so in FDM also, or we can tell atom probe tomography also, you can actually use the crystallographic features within the specimen to determine the kf. Okay, for example, if you have an alloy, and if you know that if you have two kinds of precipitates which are crystallographically on certain planes, and you know that the angle between these two precipitates is theta, which doesn't change due to the it's on the nature of crystallographic nature of those precipitates. So you know that the theta is constant between the precipitate 1 and precipitate 2. You can actually use this feature and the theta to actually calibrate the kf value for that optimum value. In the last class, I have shown you an example of how the spherical morphology of the precipitates can be used to estimate the k value, field effect. Similarly, we can use the angle between any of the crystallographic plates or the crystallographic precipitates or phases, which is a constant, which doesn't change, that can be used to calibrate the kf value. Okay, so once these planes are identified, okay, and this spacing between these planes also can be calibrated in the depth dimension. Okay, so this is one way of doing the calibration. So another way is if you have a pole. In the last class, I have shown you an atomic planes which in the reconstruction. Okay, and these atomic planes have a certain pole, either it is a 100 or 110 crystallographic axis. And if you know the material, for example, if it is a aluminum, so we know that the 100, the d spacing of 100 of aluminum is known. Okay, so it might be around 4.03 Armstrongs, correct? And this particular value, assuming 4 Armstrongs, d spacing, this value can be used as a constant value, and you can calibrate your kf. You can calibrate your kf to the need, so that your reconstruction is done in such a way that at different values of kf values, you can get a value which shows that your planes, your d spacing is near to the 4 Armstrongs or equal to the 4 Armstrongs. So this is related to, as you see in the formula, the dz kf square iron square divided by xi square. Okay, so you can see that the depth of penetration is actually proportional to the kf square, field Fe and the Ef. Here the Fe is constant, okay, and eta is known from FIM or FDM, and it means that if this dz is able to resolve this particular DHKL, you can see that the DHKL measured is proportional to the KF square. So with this, actually we can determine the KF value accurately based on the reconstruction. Okay, so we can fine tune the value of KF such that your atomic planes distance comes to a value which is equal to the d spacing of 100 plane of aluminium. With this also we can use multiple poles for calibration, so that you can actually accurately determine the KF value. Okay, so usually for high solute content, so if there is an error, so this usually is very easy for pure elements or very dilute alloys. But if you have a very high solute content alloys or multi-component alloys, okay, in that, for getting poles on the FDM field desorption images, it is very difficult. So that in those kind of alloys, we use a technique where you can see where we can use additional techniques like other additional microscopic techniques such as TEM to identify first the precipitate nature or to identify the crystallographic nature of those precipitates, and those features can be reused in the reconstruction where we can actually calibrate the KF value based on the measured value in the reconstruction. Okay, so several microstructural features which are crystallographically oriented in an alloy or the interfaces, those and the size, so we can use the orientation, we can use the size of those precipitates. If you know the size of the precipitates from a TM, then we can actually calibrate the reconstruction by changing the KF value based on the known size of the precipitates. Thickness of a thin film. Okay, so these features can be used to calibrate KF value. Okay, so we just gone through the use of FIM and FDM for better calibration to get a optimum reconstruction which mimics the actual tip surface. Okay, so I will also introduce the detector efficiency. Okay, which is a very important factor. Detector efficiency, it is nothing but related to the number of ions detected by the number of ions which get ionized or the field evaporated. So not all the atoms gets detected at the detector, because some of them they will lose to the environment, they will strike to the they will strike to the solid areas of the MCP plates and they will strike back. Okay, so they will not enter those glass tubes. So there will be a certain detector efficiency, and this can be also estimated by the crystallographic direction. Okay, this is similar to how to fine tune the KF values. So you know that if you have a interplanar spacing for any particular material, okay, so how to estimate the detector efficiency, given that if the interplanar spacing can be fixed, what we have discussed presently, if we know that DHKL can be fixed, then the ratio KF square FE square divided by efficiency and xi square, okay, the ratio fixed by the ratio between these two, numerator and the denominator. So it is possible to tune the efficiency and adjust the KF value such that your DHKL remains the same. Okay, so this is where we can actually get the efficiency. So you know that measured DHKL is proportional to KF square, So this is based on the formula of dz, okay, kf square field square divided by xi square, okay. Based on this, actually you can estimate the detector detection efficiency. Okay, so another thing is, if you have any crystallographic feature, if you have atomic planes, and if you observe the field desorption map of that particular pole, you will see these low mass density regions or the concentric rings, correct? So if you change the kf value much lower or higher, then what will happen? There will be a stretching of these planes in the reconstruction. So so if it can induce the stretching, and also it can use the shrinking on the lateral dimension of the volume, whatever you are analyzing. Okay, so if you have a pole here, it might possible that it will be stretched or it will be shrinked based on the kf non-accurate value of the kf value. So this variation in the lateral dimension of the area accompanies the variation in the measured angle between the crystallographic axis. So this is your x and z. If you see perpendicular to the reconstruction, okay, so you will have a certain poles at different location of the detector, correct? Now if we apply kf value, different value, low values to high values, then it is possible that at certain values of kf values, the particular plane at this area can be stretched. So the distance between these two poles can change, and this distance between the two poles is nothing but the crystallographic angle between the poles, correct? So that crystallographic angle cannot change, so it is measured by the cos theta. So based on this cos theta value, actually you can calibrate your kf value. Once the kf value is calibrated, actually you can use to make the DHKL same, you can actually calculate the detector efficiency. Okay, so this is the way we can estimate the detection efficiency of an atom probe. Okay, so here, for example, in old atom probes where the MCP plates are not so advanced, so they have a detection efficiency about 30 to 50%. Correct? And now in recent times it has increased to 57% for with the reflectron, and for a straight path it can go up to 72% detection efficiency. Okay. So with this, what we got, that there is the importance of calibration. What is the importance of calibration? You can see that by experiments, the xi value, ICF, KF values, R, these are all variables. These are all changing with the experiments will be performed. Okay, so that's why the calibration is very important to get a reconstruction which exactly mimics whatever the tip surface, whatever the tip volume you are analyzing, so that you will minimize the distortions during the reconstruction, so that your analysis will be optimum. Okay, so with this I will end this class, and in the next class I will discuss about the artifacts which comes during reconstruction, and this reconstruction, these artifacts comes in the reconstruction, that is everything is due to the change in electric field conditions near to the tip surface, and that is related to your tip geometry, your local variation in the radius of curvature, and presence of different kinds of precipitates or phases which is having a different evaporation field values. These all things can be related to your artifacts. So most common artifact is rollover and also the trajectory aberrations. This we'll cover in the next class. Thank you.